good, but yeah.
Hey, second block.
All right. This is why I don't record it. So. All right.
We've got Cesar in there.
You imagine if Isaac was here. You guys would be like doing derivatives still.
All right.
You get charged that back. You'd be proving that.
All right. So go to your program. Open up your program. Let's try it. So
It worked for me this time.
it's working now.
Yes.
Okay. So it had to be because you used that wrong.
Yeah, that's what it did.
Wasn't it?
Yeah, it probably was. Then I'll show you what it did when
Yeah, it definitely is because it's not in
Okay,
italics.
Okay, when I use this E, see, and
That's fine.
weirded me out though.
Why did it have to say EXP?
So you just
What
stopped
was
it.
it?
Weird.
With the X. So what do I put here? X.
Is it e to the x squared?
Yeah.
Yeah, exp is just like the function, like sine function, it's the name, right? Exp means exponential, it's the exponential function.
So that works too.
Well, evidently, when she hit the E button, it typed out exp, and my guess is that's something to do with the programming part of that. When you hit that button, inside the calculator, it's defined as the exp function, is what it is.
Is that what you have?
Joe, is that what you had, number-wise, is this 5? So you got L10, R10, T10, M10, but then that's the wrong Simpson though,
It can't. Is it all?
right? So I mean, if we did this on the quiz, which I don't anticipate probably doing this because I don't think with the press the test thing, I don't think we can access the area function anyway. So that would be an S10 right there, right? Because you said 10 subintervals. So let's, matter of fact, let's double check that. So if we go, okay, so 6, well, no,
5.
S, maybe it does, well, it doesn't.
I wrote that in this kind of test.
Well, that's what this does too.
Yeah, but Joe.
Well, redo it, hit OK, and run it again. And this time do 20. Do everything the same. Then.
I got something a little different, like 0.2002 off.
Yeah, well, it's more like the exact answer, I think, right? Because it gives the exact answer here, see? So, I don't know. I don't know. I guess I would have, well, here, I tell you, hit OK. Hit control right arrow. Let's do a little computer programming here. Keep going to 1.9. And then arrow down. This might be, no, I don't think so, because right here in Simpsons, right here it goes 0 to n minus 1. So you'd have to double that. If you put in 10 subintervals, and we really wanted to do an S20.
Just put
Since it's 0, I mean, it's
Well, I
I have a
can. I mean,
question
it could go either way. But then, so now go arrow to the right. Arrow to the right. Oh, yeah, right here.
Starts at
Well, let's say,
0.
wait a minute.
it's 2 times I.
it starts at 0 to kill the 2, so the first one's a 0.
Yeah, so the first one would be at A, which is your left edge. Okay, and then go to the next one. Go to the next one. Then when I is a 1, it would be
4, which is out in front of the function.
the 4's in the front, but then this would be 2 plus 1 times 8. So it'd be A plus 3H. I'm trying to think.
No, that'd
3.
be 2 times 2, right? 4.
No, it's
No, it's
It's-
I started at 0.
If
Now-
you got the second one, so it'd be 1.
So this would be 1, that's what I'm saying. So 2 times 1 would be 2 plus 1.
I added before and multiplied.
it makes sense.
keep going, keep going. See, then this next one doesn't have a 2 in front.
H equals 2.
H would
Because
equal
it's
2 over 220, so.
B minus A over 2n, and then in the front it was H over 3. So,
What do you get there for it?
I have to pencil that out. See, it was so long ago that I did this, and
Did you make this?
I did make the whole thing, no, but I did
He
tweak it.
stole it.
And now I'm wondering if I did that if I made that, now I'm thinking I maybe went in and did that so that if we put in 10 subminimals, it would give us S20.
You're probably smart enough to do it.
But yeah, now I'm so smart I can't remember what I did. Okay, I'm on with that. So evidently it seems to be giving us the right thing. But I don't think it's
gonna
gonna
be,
be.
because when we put it on, it still gave us the 6.
Well, that's what I mean. That's what I was wondering. When we put in 3 that time, and they gave us that error message, so I should have taken out that error message. So it gave us that error message, but then it still gave us an answer, and it was the right answer.
Yeah.
So, but any number of Simpsons should give you the right answer, but it had to work, so I must have adjusted it to make it do that. So I think that's why that looks like it does. Okay. All right. So what else? What about, so that was so finding them is easy. Okay, so we go into the program, boom, we can find them real easy. So if we ever need 10 or more, this is what we use, automatic, okay? Never have to do that many by hand. Okay, what's that in with,
Like on 7,
right?
you have the S4, but like, so when you gave us the, like 2, for like an S6, you said it was 2N3 plus T3
Right.
over 3. Does that mean that this is 2N2 plus T2 over 3?
Yes.
Just write it out. Or
Yeah, we just.
So you have an option, right? So if you want to do an S4, you need 2M2 plus T2 over 3, right? Now they ask you to do M2. So, and also automatically, if it's less than 10, you've got to do by hand, right?
To write out the whole thing.
You got to write it out,
Okay,
right?
so that kind of.
Okay, so let's be clear on that.
4-2 thing.
So 10 or more automatically go to your area program, do it. Single digits, less than 10, automatically has to be written out, okay? So when you see L4, R4, T4, M2, S4, it needs to be written out. Now it can be written out like this. Now they gave you M2, or you did M2 already, right?
Yeah.
So you either have a choice, do T2, because you didn't do T2, you did T4, right?
Yeah.
So do T2, then take your M2, put it into this, or write it out this way. So the S4, now we have a table. So it'd be B minus A, so it'd be 1 minus 0. S was what, 3N? So it'd be 3 times 4. And then it would be F of, and then you would use all 5 of those.
Number of,
N is the number of subintervals. N is always a number of subintervals. Okay, so that matches here. And then it'd be F of the first one plus 4F of, and I really don't need to write F of here because I just have these. You know, if you're given an equation, then I usually write it out in F notation, right? And then I can just take my calculator, plug in a 0, plug in whatever. But if I have a table, why write F of 0? You might as well just write 1.307, right? I mean, it's right there. The value's right there. And then 4 times 1.096 plus 4 times 1.018. No, wait, that's a 2. Plus 4 times 1.173 plus 1.435. Right, so 1 of those, 4 of those, 2 of those, 4 of those, and 1 of those. So just do that. Or you could have written out T2, which remember what T is, it's B minus A over 2N, and then it's 1 of the first one. Now remember, since we're only doing 2, they'd be 2 wide, right? So, or half wide, so you would skip that 1. So you have 1.307, you'd have 2 of the 1.018, and you'd have 1 of the 1.435. Because remember, in a trapezoid, if you're doing a T2, you're going to have 3 things in there, right? You're going to have 3 things in there. So it'd be 2 times that one.
if you're doing a T2, would you start at the So like, I don't really do it that way, I do
The actual trapezoid.
yeah.
That's fine, because remember, a trapezoid starts at the left edge, because the first trapezoid uses the left and the next one. And the last trapezoid use both
They
of
would
them.
skip the one in between
On this one,
on a T2, yeah.
well, because at the table, yeah, because you have 5 numbers there, right? So if you're only doing 2, if you're going from 1 to 0, your width is going to be 0.5, right? 1/2. So that's why you're going to go from 0 to 0.5 and then from 0.5 to 1 on your book, right? If you're looking in your book, it's a table. So that's why. So you can either do your T2, put it into here with your M2 you already found. But the key is you've got to write this out. And to be honest, most of the quiz we take next week will be writing out stuff. Most of it's going to be the less than 10. If I want you to use the program, I'm probably, well, again, if I can't, it seems to me I've had trouble in the past where when you go in the test mode, it won't let you access your other documents, so it won't let you access that area thing. You're supposed to be able to do it, but I don't know, maybe if the update will be able to, but it doesn't matter because I don't care that you can just type it into there and get that number. So what I'll probably do instead is just say, okay, M50 is this, T50 is this, L50 is this, R50 is this, and then ask you something more interesting, right? About, over, under, or whatever the case may be. Something where you actually use those. Find the amount of error, whatever. Okay, what else? What else? 28. Okay, so this has to do it, and that a big part of the quiz is going to be this true, false, must be true, might be true, right? This over, under kind of stuff. So a big part of it's going to be that. So they give you this graph right here. Okay, so what is this graph doing? It's increasing and it's concave up. So they give you these 5 numbers here, 4 numbers. Okay, which rule produced what? Okay, left, right, midpoint, trapezoid. Okay, so left, right, midpoint, trapezoid. Okay, so which one should be the littlest? The left, right? Because the lefts are going to be the most under. So L is going to be the littlest. Okay, so whatever number was the littlest is going to be L. And they're in order, I think, right? So that first number is L. Okay, what's going to be the next littlest? Because the midpoint is that tangent trapezoid. It's going to be under also, but not as much. So the next one is going to be M. Which one's going to be next? Trapezoid is going to be over, but barely over, right? It's going to be like that. And then rights are going to be way over, right? I mean, they're going to be, well, depending how many you have, but they're going to be over more than a trapezoid. So it has to do with the concavity. It has to do with the increasing, and we just want to be able to understand. So a lot of different ways I can ask you that, those things. Okay, let's run through 35 through 46 just because they are so important. So if we have one that's positive and concave up, so what's that mean, positive and concave up? Something like that, right? Something like that. It's above the x-axis, concave up. Do we know if it's increasing or decreasing? Could be either one, right? So is a right less than the exact area? Might be, right? The rights over here are going to be under, but the rights over here are going to be over. Okay, so it might be. Our midpoint's going to be under. Midpoints are definitely under. Left's less than rights. Might be. Okay, left's less than trapezoids. Might be, right? Because trapezoids are going to be what? They're going to be over. Trapezoids are going to be over for sure, right? But lefts could be over, and they could be over more, right? Could be over more. Especially if we only had, if we only had it be decreasing, right? Then lefts would be way over. So they could be bigger, but they could be lefts too, so it's maybe. 38, rights less than midpoints. Maybe, right? Because midpoints are going to be under, but rights could be way under, especially if it was on this side. Rights would be way under, okay? Are rights less than trapezoids? Maybe. Are trapezoids less than midpoints? Can't be, right? Can't be. Midpoints have to be. Okay, then we get one that's positive, decreasing, and concave down. So now that becomes like the one we were just doing. Now it's like that, right? So now, are rights less than the exact area? For sure. Trapezoids less than the exact area? Must be true. Lefts less than rights? Cannot. Lefts have to be over and rights would be under. Lefts less than trapezoids? Can, because left's got to be the most over, right? Of any of those. Rights less than midpoints? Must be true. Rights are going to be way under, most under. And trapezoids less than midpoints? Must be true. Trapezoids will be under, midpoints will be over, because midpoints are going to be that tangent trapezoid like that. And a trapezoid's actually going to be under like that, right? Okay? All right. So that's important to be able to do. And then I don't know, what about 60? What was that about?
I didn't really get that. It was, you know, we used the other graph, but it was the antiderivative.
Yeah, so you had this graph over here on 26 that did this, and this was little f, right? So 60 says big F is the antiderivative. Would T100 underestimate or overestimate? Okay, so what would big F be? Well, let's think of the chart. So if we think of the chart, this is the little f graph, right? What is the little f graph? It's positive, right? So what would this graph be? Increasing, right? This graph is also right, but look, what else is it? It's increasing. So if little f is increasing, what's big F? Concave up. And isn't that really all we need to know? I mean, this is concave down, but if little f's concave down, does that tell you anything about big F? I don't know, if you think back to the chart, it doesn't, right? So this graph is positive, which means big F is this. So what we know, but just by that, we know that big F is increasing and concave up. So if we were going to draw big F, here, it's got to be that, right? I mean, I don't know if it'd be there, but I don't know if it's positive or not. I don't know where it is, but it's got to be increasing and concave up. So therefore, what would a T100 do? A T100 trapezoid would be over. It's a chart question. It's a chart question, right? It's just, okay, here's a little f. What could you tell me about big F? And then use that to talk about trapezoid. Okay? All right. So let's go into the new thing we want to do today. So we need our calculators yet again. This is something you will for sure be doing on the quiz. Matter of fact, this will be another big part of the quiz. Okay, the quiz shouldn't be that tricky, really. You are going to have to write out some of these sums. Okay. We talked about this idea of error bounds and stuff like that. Okay, but what we're going to do today now, we're going to talk about what our goal has been all along, which is to figure out how the calculator knows how much error there is. Now it isn't really going to know how much error there is. What it's going to do is, I said this yesterday, it's going to be the worst case scenario. What's the most error there could be? What's the worst off we could be? And it's going to use it that way. So let's let's make it simple here. Let's do it with just one subdivision, one rectangle. Okay? So we're first going to investigate lefts and rights will be the same thing. Okay? Lefts and rights will be the same. So let's do this. So let's say we have this curve, right? That's going up, going down, whatever. Okay? And we're going to do a left rectangle. So here's the left edge. Now let's call this, we can call this side A, we can call this B, whatever. But it's actually just going to be one subinterval. So it's really, I probably shouldn't call it A and B because it's going to be A to B would be the whole interval. So this would be like one subinterval. Okay, so this could be like x sub 0 and x sub 1 or whatever. All right, so this would be the width right here. So here's our one rectangle here in blue. Okay, that's our one rectangle. How much is that left rectangle off? Okay, well, it's this gray area. That's how much it's off, right? Now, what did we say causes a rectangle to be off of the exact area? What causes a rectangle not to be the exact area?
Suspects that it's horizontal.
If the graph's not horizontal, right? If it has some slope. And what causes it to be more off? The steeper it is. So what if, yeah, well, we'll get to curving. So what if we went into this graph and we found where it was the steepest, let's say right there. Right? Isn't that possible? Couldn't we go to a graph and find its steepest point? Now, actually, where would that be at? An inflection point, right? An inflection point is where a graph's steepest. So we could go through and we could find on a function, we could find its steepest point. Now, we're just going to do it in this one subinterval. We wouldn't want to, if we were doing 100 left rectangles, we wouldn't want to go into all 100 subintervals and find the steepest piece, okay? We don't want to work that hard at it. So we're going to find the steepest slope, and we're going to call that K1. So in your notes, you're going to probably want to work through this with me. So we're going to call that K1. Now K1 is going to be our max slope. Now, I'm going to write it like this. Absolute value of f prime. Because the steepest slope might be negative, right? It might be negative. So it might go down like this, right? But, and that also causes a left to be off, right? If it goes down, then the left is going to be too big by that amount. And if it's positive, then the left is going to be too little by that amount. It works the same way with right. So I don't really care about over or under right now. So I'm doing absolute value. So what I'm looking for is the absolute value of f prime. I'm looking for the max of the absolute value of f prime. Okay? That's what we're going to call K1. 1 for the first derivative. It's f prime, first derivative. Now, we're going to pretend then that blue graph doesn't do this. We're going to pretend that blue graph goes up at that slope. Notice what I have drawn it here. We're going to pretend that graph goes up at that slope the whole time. Make sense? That's our worst case scenario. Find the steepest slope and then pretend that graph goes up at that slope the whole time. So that's this line right here. Let's do that in red. So instead of the blue graph going like this and having this gray area, we're going to pretend it goes up like this. Okay? So this red is our error, right? That red is our error. That's the amount that we're off. Okay? So what we need is, what is that area? What is the area of that red triangle? Okay? So the area so our error, and this is, we're going to call this our max error. Right? Now remember, back on this page, right? In this box was our max error. If we want, right, this is our amount of error, we want it to be less than or equal to that. Okay? On this side goes our max error. Well, that's what we're finding right now. The most our rectangles can be off. Probably not going to be off that much. Right? Remember what we're doing here. We're finding the steepest slope and we're pretending it has that slope the whole time. Most graphs do not. You know, they vary. Okay, so we're finding the steepest slope we can find. Okay, so what would be the area of that triangle? Well, it would be 1/2 the base times the height. Right? So what is the base of that triangle? It's right here. That's the width. Well, what's our formula for width? B minus A over n. It'd be this width. Well, we can really write x1 minus x0, but we'll just call it b minus a. It'd be easier. Because at the end of the day, we're going to just do it for the whole width. So we're going to actually say, okay, let's say we had one left rectangle for the whole width, right? What's the most it can be on? And then what's the height? What's this height here? Well, yeah, we could do all kinds of things with like trig or, I don't really want to bring that in, but here's what I'm going to do. What we do have is this, I do want to involve this guy right here, the slope. Well, K1, since K1 is the slope of this line, isn't it equal to rise over run? Right? K1 is the rise over run of this line right here. Okay? And what's the run? What did we just name the run? That was delta x, right? I'm going to use delta x here for a second, then I'll switch it, right? So couldn't I just multiply delta x over to this side? So would it be delta x times K1? Wouldn't that equal the rise? And isn't that's what this is the rise, right? So delta x, which would be b minus a over n, times K1 is what that rise would be. That'd be this height right here. So our max error, when I put this all together, is going to be K1, it's going to be b minus a squared over 2n squared, right? Remember, n is my number of subdivisions. Okay, b minus a is my width. But now that's for only one subdivision. So now I need to multiply that by n subdivisions. Okay? This is one subdivision here. This is the error for one subdivision. I'm going to multiply that by n subdivision. Now, you got to understand that K1 might be different in all those subdivisions. So what we're going to say is we're going to say K1 is the max slope of the whole thing. We're going to look at the whole interval, A to B, and we're going to find the max slope, and we're going to use that as our K1. Okay? And so therefore, when we multiply that, that's going to cancel that right there. Okay? And so we're going to get this formula. So the error-bound formula is this right here. I minus L sub n, and it could also be R sub n, right? It could be R sub n also, is less than or equal to K1 times b minus a squared all over 2n. And then write a little note to yourself that K1 is the max of the absolute value of f prime. And that's pretty powerful because it gives us a way to guarantee that we can't be off by more than a certain amount. And that will let us say how many rectangles do we need to be sure we're accurate to a certain amount. Okay, so let's do two types of problems with this. Well, we'll do one type with this, then we'll go on to our trapezoid midpoint formula and look at a couple situations there. Okay, so let's say we had the integral. I think I'm going to do okay, let's say we have the integral from 0 to 1 sine of x squared dx, okay, which we can't do the antiderivative, right? We get on our calculator and we can do it, right? We can see what the calculator says for this. But let's do what would the question be? The question is going to talk about, in your book, this formula is theorem 3. So a lot of the homework is going to say, find the theorem 3 error bound. Well, I'm not going to ask that on the quiz, right? It's just this book that calls it theorem 3. But find the theorem 3 error bound. So when they say that, they're saying use this formula. Okay? But to me, it's an error bound, or it's a max error bound formula, or max error, whatever. Okay? So let's find it for an L10. So let's find the max error for 10 left rectangles for this function right here. Okay? So what are we going to do? We're going to say, okay, I minus L10 is less than or equal to, and now we're going to use this formula. Now let me show you how I'm going to grade this, because you get to use your calculator for a lot of this. So the way I'm going to grade this and see that you're using your formula is you're going to have to show your work here. So I'm going to put a box right here for K1. Okay, we'll get to finding K1 here in a minute. And then what am I gonna have in here? So for this problem, it'll be 1 minus 0 squared over
Two
2
times
times 10, right? 2n. 2n. N is the number of subdivisions, right? We have 10 subdivisions. Okay? And I'm going to really be, I'm going to check your final, you're going to get graded on your final answer, but I'm really going to be looking for what did you have in that box right there. And that's what we got to talk about. Because what does it mean to max? Okay, so everybody get on your calculators. Okay? So here's our f function right here, sine of x squared. So what we need, so let's go ahead and get out of that and just go into your scratch pad. Emily, go to a graph. So we are going to go to a graph screen. We are going to want to go to a graph screen. And what are we going to, I'm not going to make you do derivative. I'm not going to make you find the max of f prime by doing the first, second derivative, finding the inflection points. We're not going to do all that. We're going to let the calculator do most of this work for us. So you've got to know how to do this on your calculator. So how am I going to find the max of f prime of this graph? What do you think? Don't overthink it. It's not that hard.
So just do our max. It's not for sine of x squared.
So what? No. I don't want the max of sine of x squared. What do I want the max of?
Well, I mean, do the derivative.
Do the derivative. I would do that on a calculator plate. We want that. You got to understand it. K1 is the max of absolute value of f prime. So the first thing we need is f prime. So I would probably just go on the calculator page. Now, it's pretty easy. I mean, I hope everybody can just do that. It's cosine of x squared times 2x, right? I mean, so you can either, but if it's more complicated than that, Emily, so you could just do the derivative right here. So go do the derivative real quick. But you wouldn't have to. Other way. Derivative. There you go. So if it's more complicated, you want to do it here. So you go in here and do the derivative of sine x squared. Okay, then you could copy that. You could arrow up to highlight it. You could Control C to copy. Okay, you could go to your graph page. We don't want that graph, so let's get that out of there. We don't want the f graph, right? We just want f prime. And so paste that in there. Control V. Okay, there it is. Okay. Now, okay, so we got f prime in it. Now what do we want to do? We don't want the inflection point of this graph. But the max of it. Okay, so she's got f prime up there. Okay, only from 0 to 1. I agree. And I showed you something yesterday. When you know where you want to do the graph, what do? We go 0 to 1. We do, I mean, you can probably do it from there. I like zoom fit. Now this is a pretty easy one. Now, okay, and then you can arrow. And if you're careful, slowly, boom, there it is. Now, let's talk about several things here that are really important. First of all, what if this graph would have went up here and then went down below in the negatives and then come back up?
Yeah.
Because we want the max. We don't care. This is f prime, which are slopes, right? We don't care if its max slope is going up or going down. It still causes error. So if this goes up to 0.8 and then it goes down to 0.9 negative, we would want the 0.9, right? Now the other option you have when Emily graphed it is she could have put bars around it, right? You could have done absolute value. So like Emily go up to, hit tab and yeah. Now you could go in front of this. Now your probably best bet is to highlight it and then do absolute value, but you can just type ABS too. You can type ABS left parenthesis if you go ABS, left parenthesis, that was a right parenthesis, I think. Okay, so you can do that if you hit enter. Now, nothing changed, right? Nothing changed because it was always positive anyway, right? So remember, we have the max of the absolute value of f prime. So when you go to graph your f prime, maybe the smart thing is to put it into bars right away, so everything's positive. But just understand, right, we want the biggest value. So if it goes negative and that's bigger than the biggest positive, you do it. Okay, so trace back to that again. Is that it? You sure?
Yeah.
Why doesn't it say max? There you go. Okay, that's it. Now, another thing that's very important with this number. So what are we going to put into our box on that other page for K1 right now? Is it this number or is it this number? It's this number, right? This number is the slope, right? This number is the f prime. This number is the slope. So what are you going to put in there?
1.28.
Is that 367? Is that what that is? No. If you put 1.28367, you're going to get it wrong. No. No, it's f of this. Is that it's not f of, it's f prime.
Would you put that back 8.08, 8.808252 back into the code?
No, we don't want that f value. We want this number, right? But what is that number representing? Yeah, but what else? What do you mean? What slope? The max slope. Now, I don't know, because we can only see 5 decimal places, I don't know what comes after this 7. It might be a 2. So is 1.28367 the max slope? Not if there's a 2 after this, because 1.28367 is bigger than 1.28367.
So if you put a 2 in the 808.252 for that graph,
Well, that's what this number is, though. Yeah, forget this. Forget this.
No,
We're not going to do anything with this.
calculate it and then get the exact, or like.
Back on the calculator screen.
Yes.
Okay, so, okay, I'm with you. Okay, so go back to your calculator screen. Yeah, I see what you're saying. Okay, grab this. It's still not going to matter, though. My point is still what it is, so let me show you, though. But I like what you're thinking, so put a bar, okay? Now, the problem is, how many, when we do x equals here, right, with our vertical bar, how many decimal places do we put in? And if we don't put enough in, it's not going to be as exact the numbers that we got off the graph, right? So I take it back, so that's probably not a good idea. So go back to the graph and trace there. Trace there again. But I think, Joe, you said,
Just round up.
remember, this number right here, what we're looking for is a number that the slope will never be more than. That's what we want, right? The worst case scenario. So technically, couldn't you say 1.3? Couldn't you say 2? Couldn't you say 100 for K1? Now, we want a useful error bound. Right? I mean, that would be kind of silly to say, well, the max slope's 100, so will give us the most error, but the error isn't going to be close to that if you use 100, right? So we want a number that's close to this. But look at the graph. Most of the time, is f prime around 1.28? Between 0 and 1? Are the y values close to 1.28 most of the time? They're way down here, right? Now, if this graph would have been fairly flat, right? Then most of the time, the slope would have been pretty close to 1.283 something, right? So that amount of error would have been pretty close to what our error actually is, right? But if we're going to assume that the y values of this f prime graph are 1.28367, they clearly aren't, right? So would you be safe probably in doing 1.28367 as your max f prime? Yes, you would be safe in that. But there's a larger point here that I'm trying to make, right? We want a number that the slope is guaranteed not to be more than, so we want to round this up. Now, here's what I would say. So Joe, back to what you were saying. Where would you round this? Well, we're so used to the 3 decimal place thing, right? But here's what I would say. It depends how big this number is, right? If my number is 0.34 something, 345, if I round up to 0.4, right, that's a fairly big change from 0.34 to 0.4, right? So if I just round up in the first decimal place with this one, if I go 1.3, it's not a huge change. But what if this number was 87.28? And then I went to 87.3. Is that a very big change? Relatively, it's not a very big change. You see what I'm saying? So the size of this number kind of dictates that a little bit. So if I had 0.11 something and I rounded that to 0.2, yeah, I've almost doubled it, right? If I had 0.11 something and I rounded to 0.2, I've almost doubled it. So to me, that would not be a good idea. But if I had 87.111 and I went 87.2, then I think that'd be okay, right? I haven't made that big of a change, right? So you use a little bit of common sense. I would say in this one, I would probably go 1.284. I think 3 decimals wouldn't be bad here, okay? So, but if you, I'm telling you on the quiz, if you do this and you put 1.28367, you're going to lose a point. You're going to lose a point. If you just write this number down, you're going to lose a point. Because there could be another number over here that it rounded. So this could be 7.2. And then you did not give me a number that's the biggest. Okay, so, but how hard is it? All I'm saying is somewhere you better round up. Somewhere, right? Even if this would have been 3.1, you're going to round that to a 4, right? You need to round up. You need to round up. Whatever decimal place you're going to do it in, you need to round up. And then I guess I'll be the judge whether you did it good enough. If you do 1.3, I'm not sure I like that. To be honest with you, it's pretty close. I mean, I know that'd be nitpicking. But I want you to understand kind of the concept of what we're doing. We want a useful bound as we can, but we need to round up. I want a number that's matched. So let's do 1.284.
Can you do, like you could do 1.29, even less than 3?
Yeah, right. If you decided that you were going to go 2 decimal places, this 8 needs to go to a 9, even though that's just a 3, right? We're not using the rounding rules with 5 or greater, you round up. That's what we're doing. We're saying you're rounding up no matter what. So if you did 1.29, that's not bad. I'd probably accept that. I don't know. Depends what kind of mood I'm in when I'm grading.
That 8 was a 9.
Depends if it was Joe. If it was Joe, I'm probably not giving it.
Yeah, right.
If that 8 was a 9,
Could you go 1.3?
then 1.3, but I'll be honest, I usually am going to go more than that. I'll probably go 3.
Guys, tell you the truth, Mr. Clark, just give me sometimes.
All right, so what do we got here? 1.2, we said 284. Let's do that. 1.284. Okay, so now, let's go ahead and work that out on your calculator then. So it's basically 1.284 divided by 20, basically. So the key part of using this formula is finding this number, and it's you just graph f prime. This is f in here. You graph f prime, put bars around it would be good, and then find out max and make sure you round up. You do that, you're good. What do you get? 0.642. What does that tell me then about my L10 approximation? So I could go on my area program, I could find my L10 approximation, right? And what would this error bound tell me about?
It's not your error isn't anymore.
Right. So how many decimal places do I have that are accurate in that L10? That's telling me that I think that first decimal place is probably good. Right? This is how, even though we don't know the exact area, what we've done is we've found the worst case scenario for the error, and we've said, okay, if it had that much error, even then your first decimal place will be accurate. Now, chances are we have more than that. So Emily, go to your program. Let's check it real quick. So go to your program, that area program, okay? Current, just hit current. Or if you go to 4, Okay, there you go, it's highlighted. Okay, arrow back to, I think if you just go back 1 or 2, right here, hit enter.
Well,
Oop,
on
well,
6.
that's fine, go back to 1.2, that's fine. Either it's on 1.7 and it's on 1.2, I think it's both places. Okay, so let's do like 6 decimal places.
Then the sign of X squared.
Sine of x squared. Zero to 1. 10 subintervals. Okay, now what do we got? Our left is 0.26. Our exact is this. Okay, now we said our first decimal point, but rounded, right? We could say 0.3, and according to that, we've got it. Okay, but we don't have anything beyond that. Now sometimes when you look at these, your error bound's telling you, yeah, you've got 1 decimal place, that's okay, but you might end up with 2 or 3 when you compare it to what the calculator's saying the exact one is, because you're doing that worst case scenario. So sometimes you'll look at that and you'll say, oh yeah, it's got several decimal place accuracy. Okay, moving on. We got another formula we want to
What
do
you
now.
would do is, after
So
you
you
find your
find-
exact, you would add on your most, like the error that you found in 20.
Yeah, so,
Or you would subtract.
right, so if you wanted to have an error bound, so if, let's say you found L10, right? So one of these error bounds that we wrote like this, right? So we could say, all right, a lot of times I'll just let you leave it like this, that's fine, but you could also say, okay, the exact answer has to be somewhere between L10 plus 0.0642 and L10 minus 0.0642, that's what we're saying. So you could add that on or subtract that, and you know I is going to have to be in between there somewhere. Okay? All right. Now, let's write this down. Okay? Now, remember, trapezoid and midpoint, Joe, the error is dependent on what? You said it earlier.
Curviness.
I wasn't just picking on you because you're talking and not paying attention. I was picking on you because you said curviness earlier.
Well, if you did that, you'd pick on
Well, I do, don't I?
you. Something.
All right, so K2, we're going to call K, so it's the curviness. Remember we said that's the max of F double prime, right? Because we said if F double prime is 4, that's going to be more curvy, more concave than F double prime of 2. So it's the same concept. Now we're going to have to do it a little different because it's not going to make a triangle. We can't measure the curviness. So we're going to actually do it like an integral. Okay, so I'm going to run through this pretty quickly. But okay, so if K2 is our F double prime, then F prime would be the antiderivative of that. So that'd be K2 times X, right? We're okay with that? K2 is just a number. So the antiderivative of a number would be that. And then the antiderivative of that would be this. Okay? And remember we said that trapezoids and midpoints fit parabolas exactly, right? This is why. Okay? So the exact area, so if our function has K2 as its second derivative, then we could call, right, we could call this F this value here. So what we want for the amount of error is we want to take our I value. Now trapezoid and midpoint are going to be different. Left and right was the same formula. Trapezoid and midpoint, there's going to be 2 separate ones. We're going to do trapezoid. So what I need to do is I need to find my exact area and then my trapezoid area, and I need to subtract. So this is what I'm going to do. So to find my exact area, it would be the integral. Now, to make this simpler, remember we were doing 1 subdivision? We were doing 1 subdivision before, and then we multiplied by n. So we're going to do that again. Now, to make the algebra easier, I'm going to call my 1 subdivision, I'm going to say we're going from 0 to h instead of x sub 0 to x sub 1 or a to b, because it's going to make the algebra just a mess. So I'm going to call my 1 subinterval 0 to h. Okay, so I'm going to go 0 to h. That's 1 subinterval. Okay, and then I'm going to do 1/2 K2 x squared, right? So that's going to be the exact area under this function, right? Where K2 is my second derivative. Okay, and I build it because K2 is my second derivative. But what I'm doing, think what I'm doing here now. I'm saying that this function f is going to have K2 as its second derivative the whole time, right? That's the idea. That's why it's worst case scenario. Because what I'm doing is I'm building a function that has K2 as its second derivative all the time. If you do the second derivative of this, you get K2. Okay, that's why it's the worst case scenario. Okay, the graphs we deal with aren't going to have it all the time. Worst case scenario. Okay, so how would I do this? I would do the antiderivative of this, right? So I'm going to raise that to a 3, divide by 3, so that'd be 1/6 K2 x cubed from 0 to h. And then I'm going to put my h in there. So 1/6 K2 h cubed minus, and then just 0 when I put a 0 in there. So that is my exact area right there. That's my exact area of this particular function. Now, keep in mind, that's just what we did back here. There's our exact area, right, of our worst case scenario here. I'm sorry, right here. Here, this red was our worst case scenario area, and then we subtracted, okay, our rectangle, and that gave us our triangle. That's how we did it. Well, we're doing the same thing here. This is going to be my worst case scenario area, and then I'm going to subtract my trapezoid area. So what's my trapezoid going to be? Well, in one interval, my trapezoid in one subinterval is going to be 1/2. It's going to be f of 0 plus f of h times, what's the width of my one subinterval here? H, right? So that's going to be my one trapezoid right there. Okay? Well, f of 0, remember, this is f up here. This is f up here, right? So this is going to be 1/2. What's f of 0? 0. What's f of h?
1/2 hx.
1/2 K2 h squared times h, right? So what's that going to equal? 1/4 K2 h cubed. Okay? That's going to be my trapezoid. Now, when I subtract these, right? When I subtract these, it doesn't matter what order I subtract them, right? Positive, negative, that just means over and under. Okay, so to subtract these, this is going to work out nice because aren't they like terms?
Yes.
So all I need to do is get a common denominator here, right? Well, this would be 2/12 and this would be 3/12. So when I do I minus t, I'm going to get let's just use positive, 1/12 K2 h cubed, right? I'm going to go to a new page because I'm running out of room here. Okay, so my max error seems to be, remember, this is my worst case scenario because I built this function as a function that had K2 as its second derivative, its curviness all the time. But it's going to be the max curviness, right? So it's worst case scenario. So it was, what was it? 1/2 K2. Now what was h again? H was our width. So another name for our width is b minus a over, no, it was 1/12, wasn't it? Yeah, 1/12. B minus a over n. So can I replace the h with b minus a over n? Now that's only for one subdivision though. So I can multiply that by n. So,
How come you just put minus a?
what's that?
Why'd you put minus a?
In place of the h. H was 0 to h. That was one width. Well, another way of writing one width is b minus a over n. Okay? So what do we get? So on top, so our max error is going to be, on top we're going to have K2. We're going to have b minus a cubed over what? 12n squared. Now, we could go through something very similar for midpoint. I'm not going to. And it would look just like this. Except it would have a 24 down here. Now, remember what I told you about midpoints compared to trapezoids? Midpoint was roughly twice as accurate. And so therefore the error should be about half as much. And sure enough, in the error formula, it comes out to be about half as much. Okay, so you got it. You're going to have to memorize these. Okay, you're going to have to know these. I think. don't know, maybe I'll put them on there. I might put them
Don't.
on. We'll see. Don't, yeah, they're easy.
We'll bring you, Emily will bring you some cookies. And
Okay, so in summary, this is what we had. Okay, so for lefts and rights, it's determined by the slope. The max error is determined by the slope, which is f prime. So we do the max of the absolute value of f prime, because we don't care if it's positive slope or negative slope. We'll use positive slope. And we put that k1 value in here. We put our b minus a and our n, because we're going to know how many subdivisions we're doing, right? And we're going to know our total interval. And then midpoint is this, trapezoid is this. But the key there is we use k2, and k2 is the max of f double prime. But we'll do the same thing. We're going to do one here. We'll graph the second derivative. We want to find the max, and we're going to pick that number. We're going to round up. Okay? So let's do that same integral we had. So 0 to 1, sine of x squared, dx, and let's do a t10. Okay, so Joe, do your program and do t10 for us while Emily's going to graph our second derivative. Okay, so Emily, go to your calculator screen first, and now to get your second derivative, a quick way, yeah, go there and do that. That's second derivative right there. Okay, second derivative,
What was it again?
sine of x squared, same function. So we can go right to second derivative. Now we already had the derivative for that one, but you might not always have done the derivative already. So there's a second derivative, right? So that's why it's nice, because otherwise you'd have to do a product rule. If you weren't going to use your calculator, you'd have to do a product rule, because it was 2x times cosine x squared. You'd have to do a product rule. So there I would copy and paste that, or type it in, but it's a lot easier to copy and paste. So Control C and Control V. Now, if you want to do your absolute value first, it's not a bad idea. The absolute value is in that same place where you did derivative. Remember, it's not your vertical bar, or you can just type ABS. So you can go ABS parentheses, then do Control V to paste that in.
How many separate variables do
We're doing T10. T10. Okay, so she put the bar around it, see, which is nice, because it looks like, now, what does she need to do yet? Needs to change her window 0 to 1. Because it did look like it changed on her a little bit. We'll make sure we go 0 to 1.
Do the zoom fit.
Then the zoom fit, right? Because we got to be able to, the zoom fit lets you see all the y values. It just fits your y values in there. Okay? Now notice what happened, right? Notice what happened. It took this part and bounced it, right? This part was down here, right? So if we wouldn't have put the bars around it, and we'd have done our zoom fit, we'd have had to trace up here, and then we'd have had to trace down here to see which one was higher. Well, it looks like at your right edge is higher, isn't it? So I would just trace right at 1. I would just type in a 1, because if we can tell, it's going to be at that right edge. Right? So that's what we want. Right? We could tell that was higher. Now you could type in a 0 right now. Type in a 0. That's the only other place it would have been higher, probably. And that was just 2. Right? If you trace to the right a little bit, let's see if it's going down. Yeah, I think it's going down that whole time. But it'd be good to make sure. Now just type in a 1. So let's go back to the right edge. Now this was actually negative, right? Because the absolute value flipped this up. We can tell because that sharp point there, it flipped this up. So it was actually negative, but so it's concave down, but we don't care about that, okay? So what number are we going to pick here? I like 286, right? 3 decimals is a lot of times pretty good. So 286, so 2.286. So our formula, I minus T10 is less than or equal to, in the box is going to go our K2, and what do we say, 2.286. I don't care if you write a box, make a box or not, but that is the number I'm going to be looking at. You'll get graded on that number right there when you're using these formulas. Okay, and then what do we got? 1 minus 0 cubed. Now, and here's the key. You got to make sure you understand, am I doing trapezoid or midpoint? Because trapezoid is 12, midpoint is 24. And then it's 10 squared. Okay? And you do all that, what do you get? And what'd you get for T10? Joe? How much? That's all? There was no more decimal places than that? Oh, did you just say that? Okay.
It's Jesse's fault.
Run it again and do 6 and see what it says. What are we getting for this number here? Okay, so let's don't write it like that. On the quiz, I do not want scientific notation. I don't want calculator notation. I want a decimal. So it'd be 3 zeros. 1905. So we would feel really good about 2 decimal places. So in this answer that we have, the 3-1 should be good. Now this last 0, we can't always assume because there might be a rounding like we saw in the last example. So what do you got, Joe?
I've read to put a parentheses on the x squared.
Oh, okay. Okay, so that is going to tell us, what do you got?
31117.
All right, so we feel really good about the 3-1, and then this one could be rounded or whatever, but, right? So we actually, why do we feel really good? We have a guarantee, because we know that the second derivative will never be more than this number. We know that's the most curvy it can be. We've assumed the error with it being that amount of curviness the whole time, and if it does have that amount of curviness, this is how much it's going to be off. Well, we know it doesn't have that amount of curviness the whole time, so therefore it's probably closer than that. Now, what did it say the exact one was, Joe? You still have it up?
0.310268.
310268. Well, it's, again, our first 2 were good, and our third one was off at random. So it's doing a good job of giving us that. Now, here's the last thing you have to be able to do, and this is probably the most important, because this is what the calculator does. So how is the calculator getting this number that we're calling the exact value? Because remember, we don't know this antiderivative. So there really is no exact value to be found. What your calculator is really doing is it's behind the scenes doing a trapezoid, but it's not. It's probably doing some Simpsons or some version of that. But it's when you type in this integral and ask it to do it, it's saying, oh, I can't do an antiderivative. I better do an approximation, and it's asking itself, which is a really strange conversation, but it's saying, okay, how many subdivisions do I need? For this integral, how many subdivisions do I need so I can go out to 12 places accurately? That's how it's doing it. So, let's do that. So this same problem, sine of x squared, dx, right small. So let's say, so the question would be this. Let's do it with trapezoids. We already found that K2, so we don't need to redo it. Here would be what the problem would look like. How many trapezoids do you need to get 3 decimal place accuracy? This is how you could guarantee 3 decimal place accuracy if you went with 0005. Or it might be 0001 or whatever. So now we're asking, so now I'm giving you the max error here. And I'm asking how many n's, what should n be, so that you get that. Okay? Well, it's easy. We take our formula. The only thing that will change in this is what? We won't plug in a 10 there, we'll plug in a n. So we will, what we use, 2.286, so we've already done that part. But if we hadn't, what we're going to do is we're basically going to set our formula equal to 0.0005. Now we actually want it to be, less than or equal to 0.05, but that's, right, that's beside it. Well, let me do that. Let me put, we don't want it to equal, let's say we want it to be less than or equal to 0.05. We want our max error to be less than or equal to 0.05. So 2.86, 1 minus 0 cubed, over 12n squared, right? Now, you can go ahead and do that as a solve right now. You can just do that as a solve right now in your calculator. you can tell what's gonna happen is the ends are gonna go over here, so you're gonna end up with n greater than or equal to some number, and that makes sense. You're gonna find the number of rectangles, or excuse me, trapezoids that'll work. You could do more, right? But this is what we're looking for. Comma X. Don't forget comma X. No, you don't need a vertical bar.
Just that.
Yeah, just comma, small, just comma X.
So it'd be 20.
Okay, so again, talk about the rounding. This is saying that 19.519 rectangles would do it, right? Well, we can't do half a rectangle. Would 19 do it? Wouldn't do it, so it's got to round up. So even if, back to Emily's earlier question, if this said 19.1 something, we would put what? 20, we would round up. Because, again, you go back to this, it says greater than or equal to, but it's got to be a whole number. So we're going to do, so 19.5, da, 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 da. So you're going to say 20. You're going to say 20, or it'd actually be good to say n greater than or equal to 20. Okay, so 20 rectangles would guarantee us 3. Now we did, or not rectangles, trapezoids. We did 10, and we got 2 decimal place accuracy. Well, they're saying 20 would guarantee it. So the calculator behind the scenes, when you put in a definite integral, and it says, hey, I can't do the antiderivative, it does a number of calculations. All of these can be found, right? Second derivative, find the max of it, use that value, plug it into a formula, figure out how many rectangles it needs, run a little routine that will do an approximation using that many rectangles, and it'll give you, spit out the answer that it'll know will be accurate, at least for that many. Probably get a few extra accurate places, but for sure it'll be that many. Okay? All right. Joe?
Calculator just choose infinity.
Run it again with 20. Emily, do the integral. Just do the integral of sine x squared from 0 to 1.
Which one do you want to know?
Okay? I want to know trapezoid for 20. 494. Right? So we didn't get any bonus ones, but we got 3. Right? So the formula told us 20 trapezoids would be guaranteed to give us 3 decimal place, 0.0005. And it did. Okay? Because we're assuming the calculator is working right, and it's given us all however many of those there is. What, 6? Was it 12? I think there's 12 of them. Okay? All right. Max, go ahead.
Hey, Will has a really interesting fact he wants to share with you.
I bet.
To get 10 decimal points, how many?
I'm glad that one yard.
61,726.
Next time Joe says, can I just get the first one? Say that again. You did it for how many?
10 decimal points. 61,726.
I don't know if I
Trapezoids?
Yeah,
That was for trapezoids.
I don't know if I trust Will.
it's not me, it's the calculator.
Well, yeah. All you got to do, Emily's got it up here. Emily, arrow up here.
I just changed the.
Yeah, you just change the number on the left side. So grab that and then delete the 4. Delete that.
Put 200.
So let's go point. How many did you do?
I just did e to the negative 11 to get.
Yeah, so just go 10 zeros and then 5. 61,726
Yes.
rectangles or trapezoid, would get it for us. Now, if we did midpoints, what would you expect if we did the midpoint formula? Be the same K2 value, but this would be 24.
Just try it.
So you should only need half, but go ahead and do it, yeah, but you should only need half, so if you arrow up and just change that 12 to a
It's not
24. It's not half?
No.
Better be. Oh. Oh, yeah, because then you do the square root. Yeah, because it's in the square root of that. So when you divide by 24, because you'd have 24x squared over here, when you go to solve it, you're going to divide by that 24 times that number. So it is going to be different. 43,647 midpoints would do it. Okay?
So what's the torture for them?
Simpson, I'm waiting for you to just have to wait. Here's the interesting thing. Remember I said Simpsons fits a or a quadratic perfectly? It turns out that Simpsons also fits a cubic. So, was there? So, it turns out that the fourth derivative, if you want to do an error formula, we're not going to do it, but we could, but I mean, it'd be easy, it's the same thing. The error formula for Simpson would have K4 be the max of the fourth derivative, right? And it would turn out, if we wanted to do, if we looked that up and we asked for 10 decimal place accuracy here for Simpson, it would be way less. I mean, Simpson would probably need under 1,000. Guessing, but to get it.
Can we look it up and try it?
Well, we can. Joe, it's the next line. Okay, and then we're going to work on sample 3. We're going to work on sample 3 and that project. And sample 3 needs to be getting pretty much done. So for Monday, well, Tuesday, I said. No, the project we won't turn in until Thursday. But sample 3, now we're probably not going to turn it in, but we're going to be moving on to other packets. So sample 3 needs to be pretty much done by first part of next week. And then the project will be due Thursday to tomorrow, so tomorrow's will be worked on that. Okay, so
are we ever gonna turn in the sample 1 and 2 packets to other problems?
Possibly. But I would probably give you some more work time on that before. Well, we did have quite a bit of work time. I don't know, sometime I may just, when you're driving me nuts, I may just say, hey, hand in sample 1. Here's the formula for Simpson. Okay, so if you take that same problem, no, but I was just saying how much fewer Simpson would need to get 10-digit accuracies. So,
Wait, go back to
So-
the Simpson menu.
well, hang on here a second. So yeah, so what you need is the fourth derivative. So if you did, I think on the calculator, I'll come back to it. So on the calculator, Emily, go to here. And you can go to this one right here. This will do the fourth derivative. So put a 4 there, and then put x, and then put sine x squared. Hit enter. Okay, now arrow up to that. Copy. Fine. Delete that.
She's got 5 fingers.
Absolute value. Paste. Enter. Taking a little time to graph that thing. Is yours graph?
Mine's
It's not even showing anything from 0 to 1.
Still thinking? Well, do zoom fit now. Go 0 to 1 in your window. Yeah, you always gotta remember when you change to a new graph, you gotta go zoom, you gotta go.
It's loading. I did zoom it.
Okay, Emily, go to your window. Go to menu,
mine
window,
just looks, that looks fine.
You just
0.
trace it at 0.
0 to 1.
Wow, the max.
Hit enter, now it's probably gonna think a little more.
It's at 0 for me.
And zoom, oh, it didn't think. Zoom fit.
Max, we're doing from 0 to 1, not the whole graph.
Yeah, from 0 to 1.
So it's at 28.
It's at 0.85207.
But what is the max?
28.429. That's revenue.
it's covered.
429.
Did you choose that
429.
one? Yeah.
Okay, so 28.429, and that's gonna be 1 minus 0 to the 5th. That's gonna be 180 n to the 4th, less than or equal to, so go to your calculator side there, Emily, and so arrow up and grab that. And so what was our number on top?
28.429.
28.429, and down here we have 180 x to the 4th.
238.
That's it, right? I knew it'd be under 1,000. So that's how much better Simpson's rule is. And so we needed 46,000 midpoint rectangles?
Yeah.
46,000 midpoint rectangles to get 10-digit accuracy. It only takes 238 subdivisions of Simpsons to guarantee 10-digit accuracy. Okay?
For 3, it is a 4.
How did do it take?
I got a question.
Not Simpson.
You guys have
Well, we did, when I learned calculus, we didn't do these error formulas because we didn't have this technology, to solve these. I mean, we'd be calculating this by hand. Well, with the TA30, I mean, we'd be doing those calculations, but to do the 4th derivative
Does
and
anyone
try to
from
find the
Eastern-
max of that. I mean,
Is anyone from
the solving and the stuff like that is.
So that's the third.
So the next line,
Yeah, I was in the moment.
Next line,
I was in
6-2.
85 now.
6-2.